glad to see you all back. So we just had lunch, so let me just summarize what I've told you this morning, because I don't remember. So I was talking about baby BMS, meaning BMS in 3D, and I spent a whole lot of time to explain what this symmetry is. And then at some point I actually moved to the quantum theory, meaning the theory of unitary irreducible representations of BMS, where unitary is the key word. That's what tells you that you're in a quantum theory. And so I started by arguing that ultra-relativistic limits of 0, 0 are, in a sense, weird, but then I actually recovered that weird ultra-relativistic limit from a more fundamental underlying theory of representations a la Poincaré, a la relativistic particles, where in particular I ended up talking about these BMS particles, which are really, well, whose Hilbert space of states is a space of wave functions on a momentum orbit or Bondi mass aspect orbit with this particular transformation law for the wave functions. And there was a whole lot of discussion about this, and then that was, what I talked about this morning. So what I'm going to talk about now is a corollary of those ideas. And there are many more possible corollaries which I could talk about, but I'm going to skip all of them and just talk about this one, which was in a sense the first one we actually worked on. So one question you might ask is, it's actually the way I myself felt at some point during my PhD. We have this whole classification of orbits and particles, and we understand it from the point of view of coordinate orbits. This is all nice, but can you actually use this to compute something? Can you use this whole construction to, tell me the value of something?
You are now unmuted.
Am I? Good, thanks. Should I do something? No, I should do nothing. Okay, all fine. Yes, so the question at some point that was bugging me was whether you could actually use this whole theory of representations to compute something that, at least as a sort of thought experiment, you could imagine measuring. Of course, you cannot measure it in practice because we don't live in 2+1 dimensions, but you can hope to say something. And so again, inspiration came from ADS3-CFT2, where a celebrated result, relatively recent result actually, it's from the 2000s, due to Giambi, Maloney, and Yin, is that if you compute the gravitational partition function, so you take the trace in the gravitational Hilbert space of, so you compute the trace of e to the minus beta h plus I theta j. So I should say this is gravity in ADS. If you compute this trace as a path integral at one loop, what you find is the following expression of this form, with a product from n going from 2 to plus infinity. Where what I'm calling Q is e to the minus beta over L plus I theta. So, okay, so this is the partition function of gravity in ADS3. And this, in fact, is nothing but the character of the vacuum representation of 0, 0 plus 0, 0. And so this is one of the seminal results on ADS3-CFT2 in the last 20 years, say, so I'm sure that I'm within the time frame of that result. And it's crucial in particular if you want to try to build, for example, the full partition function of the Hilbert space of gravity, because every primary state in your Hilbert space, every primary operator, is going to contribute roughly a partition function of this form, except that the product would start at n equals 1, in fact, to the full partition function. So if you sum over partition functions of this kind with a specific primary spectrum, you expect to reproduce some sort of full quantum gravity partition function, and so on. So this is one of the key aspects of ADS3-CFT2. And so since, this is the character of one highest representation of 0, 0, you might hope to actually compute something similar in BMS3, and also the partition function of gravity. You may also hope to be able to compute it in flat space, and then you may hope to compare the two. So what I'm going to do now is to briefly describe the analog of this matching for ADS3-CFT2, but in flat space. And when I say briefly describe, I mean that I'm not going to go through the details of the computation, not at all, but I am going to at least give you the keywords so that if you actually take a look at the papers, you can, reconstruct what I'm saying. Well, at least reconstruct the details of what I'm saying. So I'm going to proceed in 2 steps. First, I'm going to look at the gravity side of the story, and then I'm going to look at the group theoretic side of the story, and we'll see in the end that the 2 results match. So, and again, in both cases, I stress that I'm going to be quite sketchy, so please do feel free to ask questions, but it's not going to be a detailed technical computation. So on the gravity side, the computation that you have to do is the following. You want to compute trace of e to the minus beta h plus I theta j. You want to write that as a path integral, so a path integral over matrix of, essentially the Euclidean action of the gravity. So you want to compute this path integral, but you do it for metrics on R3, so on thermal Minkowski space, with an identification of the form that radius r, Euclidean time tau plus inverse temperature, and angle phi is identified with radius r, time tau, and then phi plus theta. So this yes, there's a question.
So in ADS, we know at thermal, when you turn on temperature, there is this either the graviton gas or the BTZ black hole. What would be the corresponding statement in flat space?
Graviton gas.
Just graviton, but
yeah, sure. So even in ADS, I mean, well, there's an underlying assumption here, which is that what you're really doing is that you're taking a certain gravitational background, and then you're expanding your gravitational field to so you're actually taking the Einstein-Hilbert action, and you're expanding it to quadratic order around that particular background that you've picked. And so, of course, depending on which background you choose, you're going to have a different partition function. So if you happen to choose pure thermal ADS3 with some, finite temperature and some angular potential theta, you happen to find this result. But if you were to choose, say, an orbifold, so a conical deficit where the deficit happens to be, I guess, 2 pi over an integer, then you would actually find here that the product starts at n equals 1, and the weight here would be actually a primary weight instead of c over 12. So you would get different results. And this was, well, technically when Jambi, Maloney, and Yin wrote their paper, they wrote this, but it was very easy from their paper to work out the generalization to orbifolds, for example. So you can do the same here in flat space. You could also choose to work, instead of working around Minkowski space, you can choose to work on an orbifold, meaning a conical deficit, which is symmetric enough that you can use the method of images to actually compute the partition function, and you'd get the same kinds of results. But here, for definiteness, I'm going to focus only on the vacuum module, i.e. on the boundary gravitons around pure Minkowski space, because it's simpler to describe. But effectively, you could also take conical deficits. Yes, Monica?
So just to clarify, the partition functions you're looking at are just partition functions counting perturbative gravitons above.
Exactly. Around the background. Exactly.
So
which is emphatically the reason why you find here the character of a highest weight representation of Eurozor, as opposed to a full CFT partition function.
Exactly. So
in particular, this is not modular invariant.
Yeah, okay. So if you want to get a guess for what the full partition function would be, you can sum over modular images, for example.
Exactly. Exactly. So what Maloney and Witten did at some point was to say, so actually when they wrote their paper, they didn't have this result. They said, it sort of has to be this result, so let's just take all modular transforms of this guy and sum over them and see what comes out. But then a few years later, Jambi, Maloney, and Yin actually proved that this was true. But actually proving this in ADS technically is very, very hard. It's actually much easier in flat space for obvious reasons, because, well, actually that brings me to what I wanted to say here. So you have this identification, and if you want to compute this partition function at one loop, what you're going to say is that this is really asymptotic to, here asymptotic means in the semi-classical limit. So it's going to be a classical action times a one-loop contribution, and the one-loop contribution is some product of functional determinants. And I should say that those are determinants of the metric, so of differential operators acting on the metric, and of the ghosts. And actually, the ghosts are really crucial for the computation. And so the key point is that when you compute those functional determinants in flat space, they're very simple. In ADS, they're very complicated because the metric is complicated. So actually doing this in flat space is much easier in that sense. I should stress, so that the reason I underlined the word ghosts here is the fact that we're working in 2+1 dimensional gravity. So there are no local degrees of freedom, which means that effectively there are as many ghosts as there are, for example, components of the metric, which means that naively you would say that these things have to cancel. You would imagine that if there are as many ghosts as would-be local degrees of freedom of the metric, there's no one-loop term. That would be true if you were to set this angular potential theta to 0. But emphatically, because theta is non-zero, these functional determinants are going to be sensitive to the fact that the spin of the metric, which is 2, is not the same as the spin of the ghosts, which is 1. And so this difference in spins, in the end, is going to give you a non-trivial one-loop partition function, even though there are no local degrees of freedom. And in fact, so as I said, there are as many ghost degrees of freedom as metric degrees of freedom. This is said. They don't have the same spins. And so what you find is that if I call this, so this thing, I can call it Z, the partition function at one loop. What you end up finding for the one-loop partition function is that Z at one loop equals some classical action, which you can conventionally choose to be this quantity here. This is just a matter of choosing a constant in the action. And then there's a product here starting from 2 to infinity. 1 minus e to the I n theta plus I epsilon. Now, there's one detail here I should mention. So, you know, I'm computing the partition function at finite temperature and angular potential theta. If you actually do the computation, you will see that the result diverges. In fact, you have here an infinite product starting at n equals 2 of these numbers, which for epsilon equals 0, so for purely real theta, this product doesn't converge. It doesn't make sense. So the only way that we found to actually make sense of the result was to say, well, let's add a small imaginary part to theta just to regulate the result, just to make it meaningful. And ultimately, we're cheating a bit because here we know that this comes from ADS-CFT. And in ADS-CFT, you have the same result, but then there's a term, you see, you can think of this as e to the I theta plus I epsilon, where epsilon happens to be beta over L. So you're sort of regularizing the results with the insight that you know what happens in ADS-CFT. But I want to stress that in principle, you don't have to know ADS-CFT. You can just do this computation, see that the result doesn't converge, and very naturally be led to this regularization. And in fact, I'm now going to argue that from the group theory perspective, you would essentially guess the same regularization. By the way, also one last thing. Here, the product starts at n equals 2 because I took my background to be Minkowski space. If I had taken a conical deficit with a carefully chosen opening angle, specifically such that it be an orbifold, then actually here the product would start at n equals 1. And you will have effectively a massive BMS character. But here I'm going to focus only on the vacuum module. OK, fine. So what's the BMS? So this is the gravity side of the story. And as I said, this is going to be very sketchy. So this is the end of the gravity side. Now, on the BMS side, sorry? It enters, well, if you choose your vacuum to be, the action to be normalized such that the Euclidean action of Minkowski takes this form, then given this normalization, the mass would actually enter here. Instead of having beta C2 over 24, you would effectively find something beta times, well, probably e to the minus beta times m minus C2 over 24. That's where the mass would enter. So it's really like the q to the h, q bar to the h bar in a 0-0 character. OK, so on the BMS side, what I want to do is to think of, So when I say BMS side, I really mean, let me consider this kind of representation where the orbit that I choose is the orbit of the vacuum module. So it's the orbit of the mass aspect of Minkowski space under all possible superboosts. And so I'm going to think of this trace e to the minus beta h plus I theta j as the character. So, okay, let me go step by step. Whenever we have a group representation, a character by definition is the trace of an operator in that representation. So this guy is actually a time translation, a Euclidean time translation by beta combined with a rotation by theta. So you can think of this as a group element, or even more precisely as an operator acting in the Hilbert space of gravitons, and you want to take the trace of that guy. So we think of it as a character of a time translation, a Euclidean time translation by, I guess, well, I beta, I don't know, plus minus, and a rotation by the angle theta. And those are, of course, very much, time translations and rotations are very definitely BMS group elements. So this is a BMS group element. So I'm computing a trace of a BMS representation. And so now the question is, how do you compute the character of this operator U of F alpha, given that it acts on wave functions in this way? Now, here is actually the point where you really see the sharp difference between BMS representations and Virasoro representations, because Virasoro representations have a discrete spectrum, so you can just by hand sum over states and you're fine. Here, you have a continuum of states. So how do you label them? Well, actually, there turns out to be a general formula called the Frobenius formula for all representations of this kind, which says that the trace of this operator for any group element F alpha, this is alpha, so this trace equals the integral over the orbit with respect to, with some measure d mu of the delta function with respect to mu. So, okay, as before, I'm first going to write the expression and then explain it step by step so that you know what I'm writing. So let me just write it and then I can tell you what happens. Okay, so first recall that this entire representation is based on an orbit of a momentum vector. So that's the base manifold over which we're going to integrate. This here is a measure on that manifold. What I'm calling delta mu is the Dirac distribution, the delta function associated with this measure, so that if I were just to, if I integrated d mu q delta of q, q naught, then I would just find 1 for any q naught. And this is just a translation. And then notice that this delta function here, it's a delta function of q and f dot q, so it actually localizes the integral to invariant points. Meaning, if you just look at this naively, you have the impression that I have to integrate over the entire orbit of all possible momenta q. But in fact, secretly, because, well, actually quite explicitly, because of this delta function here, I really only have to integrate over only those points such that f dot q equals q. And so, in fact, this is equal to, well, I guess you could write a sum over fixed points. So I'm going to call those fixed points p, e to the IP alpha. Those are the translation contributions, times a one-loop contribution of the form determinant 1 over identity minus f evaluated at p. And now, what is magical here is that for, in fact, a mass, so in principle, this is the general formula for this thing. Of course, in general, this sum might actually be an integral if you're unlucky, and it so happens that you have an infinity of points where q equals f of q, f times q. But it so happens that for massive representations, or also for the vacuum, so for massive or vacuum representations of BMS, actually there is, so there's a unique fixed point P. And it happens to be, if you remember the structure of these orbits, I'm not supposed to draw there. So if you remember the structure of these orbits, they were sort of like hyperboloids in energy momentum space, where we had energy here and then non-zero momenta there. The only point that's actually rotation invariant on this orbit is this guy here, right? Even intuitively, you can sort of see it. If you act on any point that has a non-zero, well, a non-constant, how do you call this? A non-constant Bondi mass aspect, you're going to rotate it non-trivially, and so it's not going to be left invariant by all rotations. So the only point that's actually left invariant by all rotations, i.e. that on which you localize because of the fact that theta is non-zero here, the only point that satisfies this is the tip of the hyperbola. And so this sum over fixed points actually becomes just one point. And at that point, what you find is e to the I p alpha. And now this one determinant here. So wait, first. Actually, let me simplify p alpha. I wrote it as determinant. So this is schematic. So F is typically a rotation operator, if you will. Well, a rotation map, actually, a diffeomorphism acting on the orbits. And so you can think of, this delta function here is actually a Lebesgue delta function, delta of q minus f dot q times some measure factor. And then this q minus f dot q you can think of as 1 minus f times q. Then you change variables, and you get this determinant of 1 over identity minus f. And so that's what you have to compute. But then when you actually have to compute this, this is relatively easy to do on a coadjoint orbit. What you have to realize is that every mode qm here on the orbit under rotation by theta is mapped on e to the I m theta qm, because it's a mode m. And so if you want to compute this determinant here, what you get is a product for all modes m. So now I should actually say m non-zero, 1 minus e to the I m theta, strictly speaking. Now, this is for a massive, so here I'm assuming that I have a massive representation. If I had a vacuum representation, here I would have m different from 0 and also different from plus or minus 1. And again, this result it is not actually finite, so the only way to make sense of it is to say that I'm going to rewrite this as a product for m going from, say, 1 to infinity of norm squared of e to the I m theta. And then so that's for a massive particle. And for a vacuum particle, you would just find the same with m equals 2 here. And this guy here, e to the I p alpha, p is the Minkowski value. So that's, C2 over 24. It's a constant. Alpha is a time translation, which is actually beta, which is actually I beta. So this is, minus I beta. So this is minus I beta times I, which is actually this guy here. And so at that point, you're done, because you have shown that you can think of this one loop partition function of gravitons, well, not gravitons, one loop partition function of boundary gravitons, really, as a character in an irreducible unitary representation of BMS. And so this, in a sense, is a first glimpse of flat space holography, if you will, because you can think of this as saying that you have done a bulk functional determinant computation, a bulk partition function computation, which happens to match a boundary BMS computation. So that's the fourth check that I wanted to complete today. And now I just have one page, which is called a conclusion. So maybe I can tell you about that. So a conclusion. Let me erase that. So to conclude,
just a question regarding your check. In the end, aren't you just checking the consistency of the symmetries, asymptotic symmetries of three-dimensional flat space, in the sense that I mean, you've gotten this BMS group by looking at asymptotic follows of gravitons, and you found this, and then now you have two different ways of computing this character, either from group theory, but it's there's no dynamical information that enters.
No, there's no dynamical information. No. So indeed, like in the purely kinematical aspects of ADS3 CFT2, this really is purely kinematical. It's just a statement on symmetries. I'm not saying, a dynamical statement would be a statement on the spectrum of primaries, for example. And I have no access to that. I don't know. In this case, the spectrum of primaries would be the spectrum of masses and spins that you have to include somehow in your full gravity Hilbert space. I have no clue what that would be. There's nothing here that gives you any insight on that, but that's also true in ADS. In ADS3, if you don't have a guide such as modular invariance, you really just don't know, or you're doing string theory, of course, which is a whole other matter, but unless you have some sort of microscopic theory that you suppose you know, you just don't know what you're doing.
But still an important consistency checks that these two ways of thinking about it.
Yes. And actually what I'm going to say now at the very, as a matter of conclusion, is that actually you can really go much further, and many of the things that in ADS3 are really considered as holography, you can also do here, and they're ultimately just kinematical. Many of them. Even things that are seemingly dynamical. And so yeah, that's in a sense where I want to conclude. The point, though, is, and that's not written in the conclusion, but it's important, I think, in terms of the literature. What I'm describing here hasn't been done in BMS4. You could try to write characters of BMS4, and you would get something, but how you actually match them to anything gravitational is not known. So it seems easy here because it's an easy group and it's very simply related to Virasoro. But ultimately, if you keep in mind that you're doing this because you're actually interested in BMS4, you realize that BMS4 is much more complicated. It's really much harder to do it. And so the hope is that studying BMS3 gives you some insight on how to actually do things for BMS4. And well, my checklist there on the right was, in a sense, a way to argue that there are at least some aspects of BMS4 that you do learn by studying BMS3, but there are also key aspects that you do not learn. So, a conclusion. So the main conclusion that I wanted you to take away is that, to a great extent, 3D flat space holography it's okay. I mean, it's something that you roughly understand to a level similar to ADS3 CFT2, at least as far as purely kinematical aspects are concerned. So you shouldn't be worried about the fact that there's a BMS group as opposed to a conformal group. You shouldn't be worried about the fact that the energy spectrum is now continuous as opposed to discrete. All this is actually part of what it should be, given the symmetry that you find, and everything seems to work. The only thing that we don't have, as we mentioned in some discussion, of course, is there is no string theory understanding. There's a very good reason why ADS-CFT was found from string theory, and it was ADS-CFT, not Minkowski BMS. So how to actually do this in string theory is very much an open question. As I argued, even though it is okay in this sense, it's similar to ADS-CFT, there's actually a very important technical difference which influences not only the way in which you ask questions, but also the questions themselves that you end up asking. And the technical difference has to do with you have to deal with the group, with the full group, as opposed to the algebra. If you just work with the algebra, you're going to miss quite a lot of the interesting structure. You really have to understand finite transformations and then work with them like you would with Poincaré, and then you can, proceed. Now, there's a bunch of aspects that I haven't discussed, so to go further. I mean, I personally haven't actually worked on BMS3 in years by now, but I know that people still work on it, and there's a bunch of things that are happening. So, for example, I haven't talked much about Carolean geometry, but there's a whole I don't know if I can call it a school of thought, but you can rephrase many of the questions I mentioned here in terms of really Carolian geometry and how you map a Lorentzian background on a Carolian background, and how BMS is natural from the Carolian perspective. And perhaps there's some interesting things there to be found, for example, in terms of characters. There's another aspect I didn't talk about at all, which is that actually this BMS symmetry also appears. So I derived BMS as an ultra-relativistic limit of 0, 0, but actually BMS, the exact same BMS algebra also appears in the non-relativistic limit of the CFT, except that the roles of J0, well, the roles of energy and angular momentum are interchanged. So what you used to call angular momentum becomes energy and vice versa. And finally, and perhaps most importantly, there's a bunch of relatively recent developments even that have to do with the symplectic structure of gravity, which I haven't talked about at all. But in fact, this symplectic structure can be derived on the one hand from pure gravity. You can do it by using, for example, the Wald formalism. But you can also, there turns out to be a way in group theory to associate a symplectic structure with any group on any of its quadrant orbits. And it turns out that the two are the same. If you actually look at the Wald symplectic structure and compare it to the group symplectic structure, they turn out to be the same. And this actually, the symplectic structure actually has physical consequences. I was going to say observable consequences, but they're not quite observable because we're in 2+1 dimensions here. But they're physical consequences, such as Berry phases. This is something I haven't talked about, but they exist very much. And perhaps more importantly, recently there were works in ADS3 gravity that were rephrasing the dynamics of boundary gravitons as what's called geometric actions. And without going into the details, these geometric actions are just a way to rewrite the action of boundary gravitons around a certain background in a way that is manifestly invariant under asymptotic symmetries. You can do this in ADS, you can also do it in flat space, and you can deduce from that this matching between characters and partition functions. So there's sort of a deep dynamical reason why this actually does work. And I presume that there's, a bunch of other things one could actually do with baby BMS, although I should say that from my perspective, the really interesting, so in a sense, I tend to think of baby BMS as roughly being understood by now. And I think that the really interesting things to be done lie in higher dimensions, in 4D BMS and the understanding of how the news interacts with the structure of these boundary gravitons and so on. So that's essentially what Andrea talked about. And yeah, so I hope there's many things to be still done. And yes, well, thanks for your attention. I'll stop here. I did say half an hour.
It is half an hour.
Yeah, right. No, exactly. It's roughly that.
Okay.
Yeah.
Could you say something about if there are some modular properties of the theory?
Mm-hmm.
Like if there is, can I get some mileage, like some Cardi type argument to get some mileage?
So indeed, I haven't actually talked about this. This is a development that, so this has been done, wow, like 8 or 9 years ago, long ago. I remember like it was yesterday, but actually I was just starting my PhD. Well, so yes, this has been done. One can derive a Cardi type formula for BMS. There's actually, so Tong has lecture notes on string theory, where he has a chapter on CFT, and he derives the Cardi formula in, I think, the simplest possible way, just from conformal transformations. Well, if you just take that argument and rerun it for BMS, so instead of using x plus and x minus coordinates, now you would use u and phi, and you would act on them with BMS transformations. You can just derive the Cardi formula in exactly the same way as you would do there. And so then what you find is that the entropy that is predicted by this Cardi formula matches the entropy that you compute gravitationally for these flat space cosmologies that I mentioned at some point. So this was done independently, as I said, I think 8 or 9 years ago by Barnish on the one hand, and Bakchi and De Tournai and another person whom I don't remember. I should. I don't remember now, but there was some other collaborator there, and they worked this out. So this exists, you can do it, and there is, yes, and there's sort of a singular limit of modular transformations in CFT. When you have modular transformations in CFT, you see, so you have a modular parameter tau, which is something like I beta over L plus theta. That's actually the guy, I wrote it here, effectively. Well, up to a factor of 2 pi, probably 1 over 2 pi. Okay, that's tau. And so this guy has a very emphatically a non-zero positive imaginary part, and so it makes sense to map it on A tau plus B over C tau plus D, where ABCD is an SL2Z matrix. But if now you take the limit of this guy where L goes to infinity, the limit is tau is essentially theta over 2 pi, which is now just a real number. It no longer has any imaginary part. And so in particular, this transformation now becomes a very badly singular transformation of theta. So this is a point where I have to say I myself never quite understood why it works, why there's I mean, I'm not sure how exactly to make sense of a modular transformation of this form, A theta plus B over C theta plus D, where both, you know, numerator and denominator are both real now, and this has a singularity at some value of theta. I guess the only way to make sense of it is to actually add a small imaginary part to theta, as I did in the character, and then I guess it's fine. In any case, if you sort of close your eyes and hope that this works and still derive the Cardi formula, you can do it, and you can match the value of entropy that you derive there with the entropy that you find gravitationally.
Okay, and the second question that I have is quite vague because I don't know much about this literature. So people talk about BMS algebra from starting from taking the tensionless limit of strings from the worksheet side. Could you say something about?
Yeah, actually, that could have been one point here. Indeed. So
then this alpha prime plays the role of L, square root of alpha prime, something like that. I mean, what's the dictionary between? I mean, this L should be related to.
Is it just alpha prime? I guess so.
Square root of alpha prime is L.
I guess so.
Like
No, but the thing that I don't know this. I had discussions about this with Piotr Turkin at some point, who worked on this, and so I have never worked on this, but I seem to recall that even in the early literature on tensionless limits of string theory, they had two ways to so they took string theory in conformal gauge. They have these two Virozoros, and then they take the limit of that, and effectively they get BMS. They didn't call it BMS at the time, but they actually got really baby BMS. But then they had this symmetry, and they didn't know how to actually implement the constraints in string theory, and they ended up finding two ways to implement those constraints. One way was effectively to build a unitary representation of BMS as I've described, and then they found that they had a continuous spectrum and, I guess, infinitely many states.
Massless high-spin states. There should be one full tower of massless high-spin states.
Yeah, something like that, yes.
Because that's what
but then there was another construction which was much more along the lines of non-relativistic Galilean CFT, where they happened to find I think a truncated state of space of string states. Okay. And this is related to the fact that there are two ways to build representations of BMS. Either you think of them as ultra-relativistic CFT, in which case you do what I did, or you think of them as non-relativistic CFT, in which case you do what Arjun Bakshi and other collaborators have done, where they really think of this as a non-relativistic CFT, and then they think of J0 as being the Hamiltonian, and so they effectively build a highest weight representation of Virozoro. So that's what I know about this tensionless string theory, and I remember having seen this subtlety in how you actually are supposed to quantize the theory, but I've never worked on it.
Thanks.
Thanks.
More questions? I actually have a question about what Shumangshu asked in the beginning about this Cardi formula. So if I remember correctly, the way that the formula is derived is you connect the so you need to have some sort of ground state, a minimum energy state,
yes,
and then you connect that to the behavior of the partition function evaluated on high energy states. So, yes. I guess here the lowest energy states would be the vacuum, like
yes,
Minkowski vacuum, and so on. And the high energy states, are these cosmologies, or what are they?
Yes. Yes.
But
yeah.
guys, if I understand correctly, have a different conformal structure,
Why you mean causal structure?
causal structure.
Yes, they are not black. Yes, exactly. Exactly.
And I think I mean
when-
also a conformal.
in other words, your question is, how should I think of a Euclidean flat space cosmology? In the same way, when you have a Euclidean BTZ black hole, it's clear what you mean. What you mean is that you're close to the horizon, you have effectively flat space where the periodicity of the angle is set by the temperature of the black hole, and then you have this sort of, I don't know, like a tube that goes to infinity, and that's your Euclidean black hole. Here, I don't know what the Euclidean flat space cosmology is. I don't know what they are.
I see. So you've basically done a Euclidean calculation, and I guess my confusion has to do with the fact that the Lorentzian continuation of states that you're sort of relating through what in using the Cardi formula, they and also different boundary structure, right? One is asymptotically null in the usual way, and if I understand correctly, cosmology looks asymptotically very different.
Wait, so this sort of goes along the lines of this. What's the Penrose diagram of a flat space cosmology?
Right. I guess maybe I can state my question in the following way. Is it correct to think that if I were to build a spectrum of say particles or whatever is allowed in these theories, some of the states that you have allowed, so one of them is the vacuum, I'm very happy with it, and this has an asymptotically Minkowski structure. But is it true that some of the states that one might think of allowing have an asymptotically different structure?
Oh, you mean that you would want to include in the phase space? Oh, I see. So you're saying that the full phase space of the theory should not include just one choice of boundary conditions, but several choices of boundary conditions. Is that
I don't know. Am I obliged to different choices of boundary conditions, or I'm just
not
confused?
that I know. Not that I know. I think
Okay,
they're all
maybe I
part of
was
the
just
same boundary conditions. In this setup, at least, they're all part of the same boundary conditions. I mean, flat space cosmologies do satisfy the same fallouts.
Oh, I see. So the
metric
asymptotic
does
structure is the same. It's just that the causal structure
exactly.
is fine.
No, exactly. Yes. So as metrics, at some point I wrote, I think it was here, the on-shell metric.
Okay,
That very much includes flat space cosmologies and Minkowski within one single framework of one single choice of falloff conditions for the metric components. So flat space cosmologies are very much part of that story. But it's the causal structure that's, and I'm not sure. I wonder if so of course it's sort of partly Minkowskian, but then I think, could it be something like this? I'm really not sure. I'm really not sure if this was the Penrose. I mean, please, don't remember this, but I'm wondering if that wasn't some sort of, I think the causal structure of these flat space cosmologies.
Okay, thanks. More questions? Okay, if not, let's thank Blagoje again for a very nice.
Thanks a lot. Yeah, thanks again for the invitation and for the questions. It was nice.